remember last time we did partial pressures, right? Partial pressures were kind of easy because what is the formula for doing partial pressures?
P1, P2, P3,
However many gases. So basically the formula is the total pressure for a gas, for a mixture of gases, is just the sum of the pressure of the individual gases, right? So if you know what your total is, and you know what the pressure of gas 1 is, you know what the pressure of gas 2 is, but you don't know the pressure of gas 3, how would you figure it out?
total minus 1 and 2 added together.
Yeah, your total minus your 1 and 2 added together. Whatever's left over is going to be your unknown gas, okay? So partial pressures is pretty easy, okay? Just the sum of the pressures. So now we're going to move on to Boyle's law. Boyle's law, and you're just in part 2 of your packet. Here's the handout. So if you could go ahead and do that data table that's there. I really think the handout that's in your packet is kind of, let me just steal yours. If you keep it open like this, you can see the handout really well and read the numbers well to be able to do that data table, okay? So I would lay it out like this so that you can see it and you can write down your
Does it matter which one we use first?
you start from the, yeah, it will, yeah, go from left to right. All right, so you're just writing down the data. You're just writing down the data from there, reading off the pressures and putting down the volumes. So Charles' law deals with what two variables? What is it? Temperature and volume. It's what you just wrote down, okay? Now, let's take a look at the graph. Now, this is a little bit weird, and you guys experienced this yesterday, okay, if you did the graph yourself. What's weird about the x-axis on here? Yeah, we've got a number that's below 0. So I can't just put 0 as in the corner, right? Because I've got a graph that has a negative sign. So, and I'm just roughly putting this. You don't put it exactly where mine is. But we have to have at least, whoops, let me get the pen. We have to have at least a negative 15 here. What do we have to have as our top number at least? For temperature, what's our top number? What is it? 80. Okay. Now, it'd be okay to put 80 at the top. You could also put 100 at the top, whatever you need, but you can't have anything less than 80. All right? Where's 0 going to fall on this? Is it going to fall in the middle, to the left, or to the right? Going to be to the what, Tanner? To the left. Okay. So now, this becomes a little bit weird to try to do this one, right? Because we got to break this up into equal parts. All right? There's 20 spaces from here to here. All right? So what did you guys, those of you who have done the graph, what did you go up by? What did you figure would be good to go up by? You did it by fives. So what they said is this is -5, -10, -5, sorry, -15, -10, -5, 0. Okay, and that does get you, what is it, what do you end up with as your top number there? 85. Okay, that works. Okay, that works really nicely. Now, do you really want to go through and number every single one of those lines? No. We're going up by fives each time, right?
Yeah.
So is there anything wrong with me doing this? I'm going to zoom in so I can write a little bit neater. So here we've got another 5. So what if I said this is -5, that line right there? Okay, I skip a line, this would be my 0. This would be what? 5. Skip a line, this would be?
15.
Skip a line, this would be?
21.
What is it?
25.
25. Skip a line, this is? So you can see how I can skip a line. I'm still going up by fives, but I'm not labeling every single line, right? It's okay to do that. So if you want to label your x-axis in that way, feel free to. It makes reading the numbers a whole lot easier than trying to cram all those numbers in there at once. There's nothing wrong with it. We're still counting by fives, and fives is very reasonable. What did you guys do for this side here? What's that? So by half each time. So this actually looks just like our other graph, right? You got up to 10. So this was 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, again, I'm just going to eat both ways. I'm going up by, in one case it's half, and the other one I'm going by fives. Now go ahead and plot your data. Plot your data on here for those 3 syringes, right? There were 4. There's just 3 of them. And then go ahead and answer the next 2 questions. And then turn your page to the next page, and then we'll continue on. So when you've got your data plotted, answer the next 2 questions, and then turn to the next page. Your line should have looked something like that. Now, not at the point where I just drew the slope of the line, okay? As temperature is going up, what's happening to my volume? Okay, it's going up. So when I look at this relation, so we're looking at Charles' law. If you're looking at your, oops, I meant to do this. Hang on, let me back up. Here, it's called a direct relationship. As one thing goes up, the other one goes in the same direction, right? What do we call it if it's opposite? As one thing goes up, the other goes down. Indirect, okay? So an indirect relationship is opposite. A direct relationship, they go in the same direction. If one goes up, the other goes up, okay? So when we have an indirect or a direct relationship, we've got this formula. Again, what do the ones stand for? All right, so first, starting, initial, beginning, before. Did I just spell beginning wrong? I think so. All right, those are all words that key you in to you've got your something is 1, V1 or T1. How about 2? So finish. I cannot spell today. Ending. After. Final. You get the idea, right? There's our starting and our ending, however you want to say it. Now, this is really important down here. I want you to put a box around it, star it, do something with it. Whenever, what am I, all together now? Whenever you do a gas law problem, repeat after me. Whenever you do a gas law problem, you must you really must convert to Kelvin. Whenever you've got Celsius, you can stop repeating now. Whenever you've got Celsius, you have to convert to Kelvin. Now it's easy. You just do what? Add 273. Okay? You cannot do a gas law problem with your temperature in Celsius. You will get the wrong answer. Okay? You have to always, whenever you see Celsius in the gas law problem, you should go, bing, got to convert that puppy. Can't use it the way it is, got to convert it. So, let's go on to looking at our, this is the same thing we did before. We're just pulling out our knowns and unknowns. An example would be, in a gas, a balloon occupies 2.25 liters at 298 K. At what temperature will the balloon expand to? 3.50 liters. What's my unknown? T2. What's V2? Liters. What's my T1? And what's my V1? All right, now, here's the thing. Notice that the next one is in Kelvin. The third one is in Celsius. When you write your answers on the blank, you need to convert the Celsius to Kelvin. So go ahead now and do those next two. And be sure to take the couple seconds to convert the Celsius to Kelvin. Okay? If you've already done this, just double check and make sure that you've converted the Celsius to Kelvin. If it's already done for you, you don't have to do it again. Now, here's the thing. To make life a little easier for you, if you're doing your answer and it's a temperature you're solving for, I'm okay with you leaving it in Kelvin. Unless the problem says your answer has to be in Celsius, you can leave it in Kelvin. Okay, you don't need to convert it back. And most of the problems don't say it has to be in Celsius, if I remember right. But just be aware that if it doesn't say, just leave it in Kelvin. I'm absolutely fine with that. All right. Now, again, back to algebra class. We've got two fractions, right? And one of these fractions is not like the other. One of these fractions is missing something. It's kind of like a Sesame Street, I think it was. It used to be something. Do you guys ever watch Sesame Street? Is that like gone? No, that's still on now, isn't it? Isn't Sesame Street still on?
I never watched this kid.
No, but it was there.
Yeah, it is.
It is still on? All right, so now back to, think back, way back to algebra. Okay? If you've got an unknown in a fraction, you cross multiply. Now, a lot of teachers, from what I hear, call this doing a butterflying it. Okay? What you're going to do is you're going to cross multiply. You're going to butterfly this side, butterfly that side, and then you're going to solve it. Now, I'm not a strong math student. When I look at it in this form, I have trouble rearranging this in my head. So I literally do have to take it, make it in one line, and then isolate my unknown, just like we did for the Boyle's law. So let me show you how you do that. So same sort of procedure. Here's my unknown. So this time I'm going to put a box around it because the question mark just looks a little crazy when you put it underneath. So that's my unknown that I just put a box around. So I'm going to butterfly it, which is going to give me V2 times T1. Now I'm ready to butterfly the other side. V1 times T2. Now remember, T2 is my unknown, so that's what I need to isolate. How do I isolate this? What do I do to isolate this? Yeah, I just slide the one next to my unknown under the rest of them. This is the same thing now as solving a Boyle's Law problem, right? So now I'm going to take that one and put it underneath. And so when I rearrange this, it's going to be V2 times T1 over V1 is equal to T2, C3PO, R2D2, Go ahead and rearrange the other two. What's that? Shift, setup. You want 8 for normal. And then 1. Yep. Once you get this in a line, after you've cross-multiplied, now it looks like a Boyle's Law problem, and my brain goes, yay, this is really easy to solve. I just move everything over, okay? So once it's to that form, it's really easy. But you got to remember to cross-multiply to get it in that form. Whatever's next to your unknown, you're just going to slide over the rest. So here's your unknown, V2. So V2 is here, and then you're going to slide. What are you sliding underneath? You know? See how, hang on one second. You've cross-multiplied this great. Let me see your pencil. So here's our unknown, right? So whatever's next to my unknown is going to slide underneath. So now this should be V2 times T1, and then divided by V2. Or sorry, T2. So it should be this. V. Oh, hang on. You've done it backwards to what I was looking for. Okay, no problem. So this was the, we want to go the other direction. So now it's V1 times T2. V2 T1. I see, you've got this. I think you actually did. Yes. All right, so I see a lot of you guys are moved right on. You're already on this problem. If you're not already on this problem, or you want to just check to make sure your answers are right, I'm going to work through it so you can kind of hear what it is. Because I'm guessing that many of you may have made a mistake. But you may not. Okay? So it says, if, are you ready? You want to just flip to the next page and you can go back and do that one. So if the temperature of a 7.91 milliliter sample of gas is 52.00 Celsius, what temperature will the gas be if the volumes change to 13.1? What is my unknown? What is my unknown?
T2.
T2. What is the volume that goes with T2? What is it? 13.1 milliliters. So that leaves me T1 and V1. Well, which one has a volume unit? Yeah, ml. So this has got to be 7.91 ml. Celsius is obviously the temperature. So it's 52.00 Celsius, and I'm going to convert that. And that's, what does that end up being? 325. Okay. So now I'm going to rearrange this. Now I'm going to take the extra step of cross-multiplying this. So I'm going to butterfly this. V1 times T2 equals T1 times V2. Now I'm going to pick out which one is my unknown. It's this one right here. So I'm going to slide this underneath. So when I rearrange my formula, it's T1 times V2 over V1 equals T2. Now I'm going to substitute my numbers in just like we did yesterday. You can write it the other way, that's fine. Yep, yep. As long as you have this format, it doesn't matter which side I have the other one on. So T1 was 325K. V2 was 13.1 milliliters. Underneath that, I've got V1, which was 7.91 milliliters. My units are canceling out. The milliliters are canceling out. What's the unit for my answer?
Okay.
K, it's the only one that's left. So what did you guys get when you put it in the calculator? What do you get? 538. Now I'm going to double check to make sure that I've got the right number of significant figures. Now here's the trick, and where some people, probably not on this one, but on other ones you may mess up. You're always going to look at your original numbers for your significant figures. So let's pretend this wasn't 52.00 Celsius. Let's say it was just 52. What would I need for my answer? 2 significant figures. You don't take it after you've added the 273. You're going to go to the original number. And that's where you're counting your significant figures. All right, just be aware of that. And that's why a lot of times I'll just underline the numbers in my problem so I remember to go back and look at those for my significant figures. So we have 3 significant figures, and that's what we need. So there's our answer. So then you guys go ahead and do the rest. I'm going to hand out the next sheet, which is Charles' Law problems, and you'll get started on that when you're done with those practice ones. So when you're finished with those practice problems, you're going to do the Charles' Law practice sheet that I just handed out.